MDM4U 5.3 Problem Solving with Combinations. In this investigation, we're looking at groups of distinct items. How many sets can you make using any number of elements of the set A, B, C, and D? So if you'd like to pause this video and try to write them each out, please do that now. So what we're going to do is look at each of the different sets of length 0, 1, 2, 3, or 4. So starting off with a subset of size 0. This is a symbol which is called the null set or empty set, meaning that it has no elements. There's a difference between the null set and 0. 0 is an actual number. The null set means that it's empty. So the number of elements in the empty set is 0. The number of elements in the set 0 is 1 because that includes 0. So we still consider this to be an element, or sorry, a subset of size 0. That's one set. Not selecting any is one case. Selecting 1, we could do A, B, C, or D. Selecting 2, we have each of these options available. Notice that we don't have A, B, and B, A as a selection because we're not interested in the different permutations. We're interested in the distinct items in a set. So AB is the only case that's written there. 3 items, that's just how many ways can we exclude one of these items. So we're excluding D, we're excluding C, we're excluding B, we're excluding A. And that's similar to how many ways can we select an item. Next, selecting 4 of these items, there's only one way to do that. So altogether, 1, 4, 6, 4, 1. Do these numbers look familiar? Ponder that. And hopefully you can spot that that is coming from Pascal's triangle. Therefore, the total number of subsets of 4 distinct items is 16. So if you recognize that this is a row of Pascal's triangle, you may recall that the sum of the row entries for any row is 2 to the power n. In this case, 2 to the 4 is equal to 16, and this holds true. But there's a deep connection between Pascal's triangle and combinations. Let's have a look. The number of groups of n distinct items of size r is equal to NCR. And that's the combination statement is equal to TNR, where lowercase t and r is a location in Pascal's triangle. So that means if you want to figure out the value of a combination, you can just find its location in Pascal's triangle. And let's take a look at an example. How many different ways are there to select 2 items from A, B, C, and D? So our size of the number of objects is 4. Our selection size is 2. NCR is 4, choose 2. And that is row 4, 0, 1, 2, 3, 4, position 2, 0, 1, 2, 6. So we can use Pascal's triangle to quickly do mental calculations with combinations. Subsets of n distinct items. So what is a subset? A subset is a set whose elements are also elements of another set. So it's any selection of the available items like we did in our investigation. The total number of ways to select any number of items of n distinct items is given by 2 to the power n. Like we saw in that example, it's kind of like the Pascal's row sums, 2 to the power n. But we can think of this as fundamental counting principle. Each choice is either selecting it or not. A set of n distinct elements has 2 to the power n subsets, including the null set. And a set of n distinct elements has 2 to the n minus 1 subsets, excluding the null set. So this example is going to do an illustration to help explain why we have this case of subtract 1 and when it applies. And how many ways can you select items to eat for lunch? So, using fundamental counting principle as the basis of our rationale, each and every single item, apple, banana, carrot, and drink, can be thought of as you are either going to select it yes or no. Yes or no. And a tree diagram can help support our conclusion here. this is equal to 2 to the power 4, which is 16. And if we count the total number of outcomes in the right column, each of these represents, each branch represents a unique outcome. And there's 16 in total. How many ways can you make a selection of at least one item? So if not selecting an item is not an option, we have to exclude one case. And if you look at our tree diagram, the branch which is the null set is no, 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 no. So that's 2 to the n minus 1 as a general formula for cases which are excluding the null set. Next. Our last example was for n distinct items, but this is for combinations with identical items. So, if at least one item is chosen, the total number of selections that can be made of A items of one kind, B items of another kind, and C items of another kind, and so on, is A plus 1 times B plus 1 times C plus 1, and so on, minus 1. So we're going to talk about each of these different factors. Each of these factors are representing the choices at a certain stage, similar to a tree diagram. And that minus 1 is still the minus 1 in the previous example where 0 items are selected. So let's see an example. Kate is in charge of stocking a coffee room at her office. She can purchase up to 3 cases of cookies, 4 cases of soft drinks, and 2 cases of coffee. How many different purchases can be made? So, fundamental counting principle tells us that we can choose 0, 1, 2, or 3 for cookies. So that's illustrated here with this tree diagram, 0, 1, 2, or 3. So what's tricky, the reason why we have this plus 1 in this formula is because even though there's 3 cases of cookies, we can also select 0. So that's 4 choices. That's the number of ways this stage in this process can be completed. Similarly, for the soft drinks, if there's 4 cases of soft drinks, that's 0, 1, 2, 3, or 4. And that's 5 choices. And lastly, coffee, 2 cases of coffee. So either 0, 1, or 2. Now altogether, this is going to be equal to 4 times 5 times 3 by fundamental counting principle. That tells us all of these cases. But we have to subtract 1 for the following case, selecting 0 cookies, 0 soft drinks, and 0 coffee. So that will exclude the empty set.